Okay, let's check out those examples. Bring it back here. So kind of the idea was when we want to start looking for where local maximums and minimums occur for our function, first thing we need to do is find critical numbers. So we're going to take a look at f of x equals 1/3 x cubed minus x squared minus 15x. Just a polynomial. Those tend to be the most straightforward. And then we'll also look at g of x, a little bit harder, x to the 2/3 times the quantity x plus 3 squared. Okay, I'm gonna change over my paper here, example. Find the critical numbers. Starting with f of x equals 1/3 x cubed minus x squared minus 15x. Okay, critical numbers, that is where our derivative equals 0 or where our derivative does not exist. So first thing we need is to know the derivative. And here with the polynomial, not too bad, right? Multiply the 3 down. Let's see, that would just be x squared minus 2x minus 15. Okay. All right. Now let's begin. Okay. Where does the derivative equal 0? Let's start with that. Let's kind of investigate this. So I'll just say, hey, let me take my derivative, x squared minus 2x minus 15, set it equal to 0, and we'll solve for x. And here we're like, okay, well, maybe this factors. If not, we could use the quadratic formula. I think this will factor. X minus 5, x plus 3 would do it. And so we'll have two solutions. X equals 5, x equals negative 3. Those would be two of our critical numbers. Don't stop there though. We also want to look at, hey, are there any x values where the derivative does not exist? For this function and this derivative, no, there are none. So in part B, we'll look at one where this will have some possibilities for x. Kind of the idea is, well, you know, when you got a polynomial, you know, even your derivative is a polynomial, that's never going to be an issue for a D&E because, you know, there's no cusps. There's no vertical asymptotes. You're never dividing by 0 in the derivative, that sort of thing. So again, we'll look at one where this will give something that'll be a little bit more clear. For now, though, we just have these two solutions, x equals 5 and x equals negative 3 are our critical numbers, both where the derivative equals 0. So the idea is, again, like these could be x values where we'd have a local max or a local min. We don't go there, we don't investigate that until the next section, 4.3. We're just kind of establishing this idea of the critical number right now. Okay, let's take a look at part B. It's a little bit more challenging. I'm gonna say, all right, how about g of x equals x to the 2/3 times x plus 3 squared. Okay, to find g prime, there are actually a couple of options. So one option, and the option I'll actually go ahead and do, is say, okay, if we want to know the derivative, let's take it as a product rule. We have this thing, x to the 2/3 being multiplied with x plus 3 squared. You could avoid the product rule if you were to multiply this out and then distribute the x to the 2/3. You could even think of it kind of like a polynomial, you know, with some fractional exponents. That said, hey, I know the product rule. I'm not going to bother multiplying that out. I'm just going to go for it. So let's do this. G prime, let's see, derivative x to the 2/3, 2/3 x to the negative 1/3. And that gets multiplied with x plus 3 squared plus x to the 2/3. And that's going to multiply with 2 x plus 3 to the first. Chain rule here, then derivative of x plus 3 times 1. And now maybe I'll clean that up just a little bit. Now that I have it, when I do this, obviously there's some easy stuff I can, kind of like not write, like times 1 into the first power. But also notice I have this negative exponent. I'm going to make this whole thing a fraction. I'm going to say, okay, in the numerator, I'll have the 2 and the x plus 3 squared. In the denominator, I'll have this 3 and x to the 1/3. So let's write it like that. And then plus, and over here, well, okay, 2 x to the 2/3 times x plus 3. And there we go. From here, we need to look at, all right, where does our derivative equal 0? Start with that. So I'll take this whole thing, 2x plus 3 squared over 3x to the 1/3 plus 2x to the 2/3 times x plus 3. That's going to equal 0. Okay. Now this looks really bad. How am I going to solve this? For x, my gosh, there's fractional exponents. There's this denominator. They're being multiplied here. Actually, if we're clever, there's one thing we can do that's going to clean this up real fast. So we notice that this first denominator is 3x squared. Why don't we multiply both sides by this denominator? Multiply both sides by 3x to the 1/3. So just that is going to change the feel of this whole thing. Right, if I multiplied the left side by 3x to the 1/3, obviously it cancels out here, and all I have left is 2x plus 3 squared. Plus, now this 3x to the 1/3 also multiplies by this term. When it does, we think, okay, well, 3 times 2 is 6. How about x to the 1/3? Think of it as multiplying with x to the 2/3. X to the 2/3 times x to the 1/3. We would add exponents. Well, 2/3 plus 1/3 is just 1. So those multiplied simply gives us 6x, and then we still have the x plus 3. Like so. Looking pretty good. What to do from here? You might think, oh, let's multiply everything out. You don't want to do that. And you don't want to do that here. There's a faster way. I guess if you did, you could still recover where this is going to go. We're going to end up factoring. In other situations, that would be a really bad idea. Like if this was a cube or something like that, you wouldn't want to multiply everything out and then try and refactor. From this point, let's think, hey, we've got these two terms. What do they have in common? This term and this term. You think, well, they have a 2 in common. There's a 2 and the 6, and then they have an x plus 3 in common. Okay, let's factor that out. 2 times x plus 3. What would that leave behind? Well, we still have an x plus 3 for this first term. And we still have a 3x for this term. And just like that, we factored, we can simplify here. 4x plus 3. And boom, look at that. I mean, how many steps? Went from this, which is, really intimidating, 1, 2, 3 steps later, we got a nice, clean factoring. And we can say, all right, so both of my factors equal to 0. And we got it, -3. And then here's subtract 3 divided by 4, x equals -3/4. And we got two critical numbers just like that. Okay. So just kind of zero in, kind of if I could reiterate anything, when you have these denominators, hey, multiply everything by that denominator, and maybe it cleans up really, really nicely. And then even if you have these two terms, hey, still think to yourself, well, what do these two terms have in common, right? If something's equal to 0, probably the fastest way, or the way, not the fastest way, but the way to solve this is to factor. So do you really want to multiply everything out first, or do you just want to, kind of take it as it is? Maybe it can be factored right away. Okay. We also need to think about, hey, when does the derivative d and e? Let me write what the derivative was again in its original derivative form. Okay, so we had like this, 3x to the 1/3. Here it was from the product rule. Okay. Think, well, what could happen that would cause this derivative to not exist? You think if this denominator right here, if that was equal to 0, right? If 3x to the 1/3 equaled 0, then our denominator would be d and e. Well, that's not too bad to solve, right? I could divide by 3, I could cube both sides, and I could end up with x equals 0. If x equals 0, that causes division by 0, we've got a d and e. So x equals 0 is one of our critical numbers as well. So let me circle all of them. We've got x equals -3, x equals -3/4, and x equals 0. Okay, just for sort of our investigation, and we might as well like use technology to kind of like see if we were right. Let me switch over here to Desmos, and let's graph this thing and see if we were onto something. So we just had our original function was, let's call it y equals x to the 2/3 x plus 3 squared. And it's got this kind of funky little shape, right? So it comes down, touches the x-axis, comes back, and then does like this bounce. Well, where are those maximums and minimums occurring, right? And we see one of them here at -3. That was one of our criticals. We see one up here. Let's see, where does that happen? Was it x equals -3/4? Yeah, it looks like it. At -3/4, it was right there at the top. And then finally, where the derivative was d and e was at 0. And yep, right there at the origin, there's a cusp, really sharp cusp, where our derivative was d and e right there. Very nice. Hey, while we got this up, I'll graph the first one that we did, part A. X cubed minus x squared, graphing the original function, 15x. Okay, we might have to zoom out a little bit. All right, so it's kind of got this sort of polynomial shape, right? This wave. We realized our criticals were at x equals 5, which, yep, that was the local min down here. And at x equals -3, and that was a local max right there on the graph. So it turned out all of the criticals that we found in both these problems were in fact either a local max or a local min, although that's not guaranteed. It did work out here. All right, you guys, well, let's stop this video. After these examples, we'll look at absolute maximums and minimums next.